Welcome to another session where we are going to discuss about computer processors, the engine that drive computation. I'm your presenter, Moshiri Nyaga. So we are going to start with understanding what is a computer processor. Although programmers tend to think of a conventional computer and often use the term processor as a synonym of a central processing unit, which is a CPU, computer architects or the people who develop computers have much broader meaning that include the processor used to control the engine in our automobile, processors in handheld devices like phones, remote controls devices, and specialized video processor are used in graphics equipment. So a processor can be defined as a digital device that can perform computation involving multiple steps. And a processor can be used to fix selectable parameters or programmable logics. Something to note is that in this presentation, whenever we talk about a processor, we will be discussing about all the architects, both the Harvard and the von Neumann, that we'll be discussing much later. So processors are used in various roles, which include number one, the core processors, the microcontrollers, embedded processors, the general purpose processors. So what is there? We can start with the first one, which is a core processor. A core processor operates in conjunction with and under the control of another processor. A core processor consists of a special purpose processor that performs a single task at a high speed. A good example of a processor that uses a core processor is known as the floating-point accelerator to speed up the execution of arithmetic operations. When a floating-point operation occurs, the CPU automatically passes the necessary value to the core processor and obtains the results, and then continues the execution. In architecture, where a running program does not know which operations are performed directly by the CPU and which operations are performed by the core processor, we say that the operation of a core processor is transparent to the software. Typically, in a nutshell, we can say the core processor used fixed or selectable logic, which means that the functions the core processor can perform are determined when the core processor is designed. I think that's clear. The other one is the microcontrollers. A microcontroller consists of programmable device dedicated to control of physical systems. For example, or a good example for the microcontrollers, learn physical systems such as the engine in modern automobile. Maybe when you talk about that, we're talking about the landing gear of an aeroplane and the automatic doors in our offices. So a microcontroller performs a trivial function that does not require much traditional computation. Instead, microcontroller test the sensors and send signal to control devices. Right? The other one is called the embedded processors. Embedded processors. Embedded processors run sophisticated, oh, okay, I don't know how to, a bit complicated electronic devices such as wireless router or smartphones. The processors used for embedded systems are usually more powerful than the processors that are used as microcontrollers, and often run a protocol stack used in communication. The processor may not require all functionality found on a general purpose CPU, right? That's a disclaimer that the processor may not contain all the functionalities found on the CPU. Obviously, I'll take you back to the basic, what are some of the functionality found in the CPU. And then the other role, or the last role, is the general purpose processors. The general purpose processors are the most familiar, and they're used in the day-to-day operations of computers, and these are the most common in our day-to-day life. Something to note is that early processors were created from the discrete logic. A modern processor is implemented as a single VLSI chip, right? If you look at the computer history, you're going to check about the very large VLSI chip, right? So we move on. So we have two major approaches of that. Anytime we talk about different types of architectures should come in your mind, right? So we have the first one, which is called the Harvard architecture, and we have the other one, which is referred to as the von Neumann architecture. The von Neumann architecture. So we can start with the first one, which we're going to discuss about, which is the Harvard architecture. The Harvard architecture refers to a memory structure in which the processors are connected to two independent memory banks via the independent memory banks via two independent set of buses. It was basically developed to overcome the bottleneck of the von Neumann architecture. The main advantage of having the separate buses for the instruction and data is that the CPU can access the instruction and read/write data at the same time. All right. So this is basically the architecture of the two architecture. The other one, the advantage of the Harvard architecture arises from its ability to have one memory unit optimized to store programs and another memory unit optimized to store data. The other demerit of using the Harvard arises from inflexibility. When purchasing a computer, an owner must choose the size of the instruction memory and the size of the data. So basically, this is the structure of the Harvard. So we move on. So von Neumann architecture. The von Neumann architecture uses a single memory to hold both programs and data. The modern computers are based on stored program concept introduced by von Neumann. I think in 1930s. The programs and data are stored in two separate storage units called the memory. So this is the structure of the von Neumann architecture. We have the memory, we have the control unit, and you can see how data is that moves. We have the accumulator, which I think we discussed a bit earlier, and we have the whole structure of the processor or the CPU. So these, whenever you're told to do a structure of the von Neumann, this is the most common one. So let's discuss. The von Neumann architecture employs a store program approach because a program is stored in the memory, you see, or mostly the ROM. More importantly, programs can be loaded into the memory just like other data items. The von Neumann architecture offers complete flexibility at any time. Any owner can change how much of the memory is devoted to a program. I think I've really explained well, and in most cases you can look at the differences of both the Harvard and the von Neumann. So we go straight to the range of processors. Because processors span based on their functionalities and have many variations depending on the work they do. So we have the first one, which is called the fixed logic processor, which is the least flexible and performs a single task. More important, all the functionality needed to perform the operation is built when the processor is created, and the functionality cannot be altered without changing the underlying hardware, right? You can see what I've just said, e.g. a fixed logic processor can be used to design or compute a function, such as a scene X, or to perform graphics operation needed in a video game, right? We have the next one, which is called a selectable logic processor. A select logic processor has slightly more flexibility compared to the fixed logic processor. In essence, a selectable logic processor contains or facilitates to perform more than one function in a specified way. When the processor is invoked, the sin X or cosine X is executed. So it can do the sin X and cosine X, so more than one processor. The next range of processor, we have the parameterized logic processor, and this adds additional flexibility compared to the selectable logic processor, and although it only computes predetermined functions, the processor accepts more parameters that controls the computation, right? We can just go to the next one. The next one is called the programmable logic processor, which offers the most flexible functionality because it allows the sequence of steps to be changed each time the processor is invoked or executed. The processor can be given a program to run, typically placing the program in the memory. So it's good to understand the basic structure of a processor, or how does this processor that we're discussing, how does it look? We have the arithmetic. We have up here. We have the internal connection, we have the arithmetic logic unit, we have the controller, we have the local storage, we have external interfaces, and then we have external connections. So we go straight and discuss the purpose of each. We have the controller. We have the first one, which is called the controller. So the controller forms the heart of the processor. The controller hardware has the overall responsibility for program execution. That is, the controller steps through the program and coordinates the action of all hardware units to perform specified operations. We have a rule, or the arithmetic logic unit. We think of the rule or the arithmetic logic unit as the main computation engine in a processor. The arithmetic logic unit performs all the computational tasks, including the integers, arithmetics operation on the binaries and bits. And here, this is where the boring operations are done, meaning the logics are here. However, something to note, arithmetic logic unit does not perform multiple steps or more than one step to initiate activity. Instead, the arithmetic logic unit only performs one operation at a time and relies on the controller to specify exactly what operation to perform on the operation of arrays. All right, so you can see we have the arithmetic logic unit. Something that is very key here we need to discuss about, haven't written or mentioned there, is the local data storage. The local data storage. A processor must have at least some local storage to hold data values, such as the operands or the operation, for arithmetic operations. And as a result, we will see how storage comes on board when we discuss about registers. So within the processor, we have to have local storage, and whenever we discuss about the registers, that's where it comes in. I haven't mentioned on my presentation here, but local data storage is a bit key. So we go straight to the internal connection, or the internal connection. A processor contains one or more hardware mechanisms that are used to transfer values between the other hardware units. For example, the interconnection of hardware is used to move data values from local storage to arithmetic logic unit, or to move results from arithmetic logic to the local storage. The architects or the users sometimes use the term data path to describe internal connection. So sometimes you might say we are talking about the data path as the internal connection. The other one is the external interface, which is very important. The external interface handles all the communication between the processor and the rest of the computer system. In particular, the external interface manages communication between the processor and the external memory and input-output devices. All right. So those are some of the structure, or how the processor is structured. So we go straight on to the next presentation, which is the role of processors. Right, the role of processors. I think this one we had mentioned a bit early, but it's good to discuss the role of processors, which the role of processors, it's we have the core processor, we have the microcontroller, which consists of the core processor operates in conjunction with and under control of another processor. Usually the core processor consists of a special purpose process that performs a single task at a high speed. The microcontroller consists of the programmable device dedicated to the control of the physical system. Embedded processor runs sophisticated electronic devices such as the wireless router or smartphone devices. General purpose processors are the most familiar and need literal explanation. For example, the CPU, we have the CPU, and the PC is the general purpose. They're used in the CPU, in the PC, right? So that's generally what we can summarize about the structure and how the CPU it looks like. So it's quite, once we understand the structure of the CPU and different architects that are used in the processor, it's good to discuss a very key element of the fetch execute cycle. How does a programmable process access and perform steps to execute a program? The underlying mechanism is basically the fetch execute cycle. So all programmable processors follow the same fundamental paradigm underlying the mechanism, which is referred to as the fetch execute cycle. To implement the fetch execute cycle, a processor must have an instruction pointer that automatically moves through the program in the memory, performing each step. Right? So at every level, a programmable implements this process. Right? So it's good to see this process of the fetch execute cycle. So and how it operates. Right? So take note on the last. Each programmable processor must execute the two basic functionality, which is fetching and executing. All right. So we go straight on to something called a program translator. A programmer uses a high level language to create a computer program. We say, or we mostly call the codes or the source code. The programmer uses the tool to translate the source code into a presentation that a processor can expect. So a programmer invokes a single tool such as the GCC that help in to perform the translation. First, a preprocessor expands the macros, producing a modified source program. The modified source program becomes an input to the compiler, which translates the program into an assembly language. Right? I think I'm trying to explain the program translation. So the modified source program becomes the input to a compiler, which translates the program into an assembly language. Although it is closer to the form needed by a processor, assembly language can be read by humans. An assembler translates the assembly language program into a relocatable object program that can contain combination of binary codes and references to external library function. A linker, which is here, a linker. Processes are the linker, a linker, which is here. Linker processes the relocatable objects program by replacing external function references with the code for the function. Right? To do so, the linker extracts the same functions, and such as one or more libraries to find the binary code for the function. Right? So these steps translate the source program to the binary code representation. I think I've tried to be as clear and brief as possible so that you're able to understand how a source code becomes its preprocessor and how the source code becomes a binary object. So that's the whole process. So we move on to something called the clock late and the instruction late. It's very good to understand the whole idea about how the clock rate and how an instruction is executed. So most processors use a clock to control the rate at which the underlying digital logic operates. Anyone who has purchased a computer knows that the sale of personnel push customers to purchase a fast clock with the argument that a higher clock rate will result into high performance. Right? So most systems, the time required for execution portion of the cycle depends on the instruction being executed. So the fetch execute cycle may not proceed to a fixed rate because the time taken to execute an instruction depends on the operation being performed. I can explain that further, that one of the primary questions about processor concerns speed. So how fast does the fetch execute cycle operate? So the answer depends on the processor, the technology used to store a program, and the time required to execute each instruction. On one hand, a processor used in a microcontroller to execute to acute a physical device, e.g., we've talked about an electric door, can be relatively slow because the response time under 1/10 of a second seems fast to a human. On the other hand, a processor used in the high-speed computers must be as fast as possible because the goal is to maximize the performance. So most processors use the clock to control the rate at which the underlying digital logic operate. Right? And as usual, the example I've given out is anyone who has purchased a computer knows that the sale personnel push for customers to purchase a fast clock with the argument the higher clock rate results into higher performance. A disclaimer though, although a higher clock rate usually means the higher processing speed, it is important to realize that the clock rate does not give the rate at which the fetch execute cycle proceed. In particular, in most systems, the time required for execute portion of the cycle depends on the instructions being executed. I think we are going to see it later on that operation involving the input-output can require significantly more time than what we think. The time also varies amongst the basic arithmetic operation, like integer multiplication and other things. So that's it, and it's good to know how to start the fetch execute cycle now that we understand about the clock rate and the instruction and how the execution is done. So how do you start the fetch, or how does the processor start the fetch execute cycle? The answer is complex because it depends on basically the underlying hardware. For example, some have a reset option. On such processor, engineers arrange the combinational circuit to apply voltage to reset line until all the system components are ready to operate. So the step used to start a processor are known as bootstraps or bootstrap. In a memory embedded environment, the program to be run usually resides in the ROM or read-only memory. On a conventional computer, the hardware reads a copy of the operating system from an input-output device. Hardware which is needed for the bootstrap, because the signal must be passed to the processor that causes the fetch execute cycle to begin. Right? So the steps used to start a processor are known as the bootstrap in an embedded environment. I think that one is clearly mentioned on this presentation. Many devices have a soft power switch, which means that the power switch does not actually turn on or off. Instead, the switch acts like the sensor. The processor can integrate the switch to determine the correct position, and the booting device that has a soft switch is no different than booting other devices. Right? So that's how the processor execute. So for me to summarize the whole presentation, I can say a processor, or I can just break it down to explain what is a processor and how it runs. So this is just a summary so that you're able to understand. So if you're asked to define what's a processor, is a digital device that can perform computation involving multiple steps. A processor can use to fix selectable parameters or programmable logic, and that's why it's referred to as an engine, which identifies the processor. Right? A processor can be classified in different ways, and the ultimate goal of the processor is to control the fetch execute cycle. So with that, I think I've tried to summarize in detail about the variety of processors and the computation engines that are used in computing. You can read more about the Harvard, the von Neumann in the corner in this book with the Essential of Computer Architecture, the 2017 edition, and you'll learn more. So thank you, and wait for more videos to understand more.